So in this video, we will study the concept of monotone sequences. So let's get started. Let xn be a sequence. We say that xn is increasing if for any natural number n, xn is always less or equal to Sn plus 1. And we say that xn is decreasing if for every natural number n, actually xn is greater or equal to Sn plus 1. So this is perhaps a much more formal way to define the concept of increasing and decreasing sequences. And more generally, a sequence which is either increasing or decreasing is called monotone or monotonic sequence. Now, I'll prove that this sequence is increasing, and so the claim is that xn is an increasing sequence, and it's easy to show this. If we let n be any natural number n, then clearly, since n is less or equal to n plus 1, then you follow that xn is less or equal to xn plus 1, and xn is an increasing sequence. Consider the following sequence where xn is equal to 1 over n for every natural number n. Now, I'll prove that this sequence is decreasing. Indeed, given a natural number n, since n is less or equal to n plus 1, then it follows that 1 over n is greater or equal to 1 over n plus 1. As a result, the sequence xn will be greater or equal to the sequence xn plus 1, and this means that xn is a decreasing sequence. The sequence negative 1 power n, and let's do a case analysis here. Case 1, assume that n is even. In this case, xn is going to be, of course, negative 1 power n, which is 1, and xn plus 1 is going to be negative 1 n plus 1, and since n plus 1 is odd, then this will be negative 1, and in this case here, xn is in fact greater or equal to xn plus 1, right? So in that case, if this is xn, then this will be xn plus 1. So this sequence, so thus the sequence is non-increasing. Thus the given sequence is non-increasing. Case 2, assume that n is odd. In this case, xn will be negative 1 power n, which is of course negative 1, and xn plus 1 is going to be negative 1 n plus 1, which is 1 since n plus 1 is even. And as a result, we'll have here that xn is in fact less or equal to xn plus 1. So we'll have a situation like this will be, for instance, xn, and this will be, for instance, xn plus 1. So in this case here, the sequence is non-decreasing. Thus, xn is non-decreasing. So we have a sequence which is not increasing and it's also not decreasing. So in summary, in light of the observations above, xn is not a monotonic sequence. A similar analysis will show the following. Assuming that n is even, we obtain that xn is of course just going to be n, and xn plus 1 is going to be n plus 1 times negative 1, so negative n plus 1. And in this case, it is clear that one is positive and the other is negative. Thus, xn is actually greater or equal to xn plus 1. So if this is xn, this will be xn plus 1. So this sequence must be non-increasing. Therefore, the given sequence is non-increasing. Assuming, on the other hand, that n is odd, then xn will be in fact just negative n, and xn plus 1 is going to be n plus 1. And of course, in this case here, xn is less or equal to xn plus 1, because one is negative and the other is positive. So you'll have a case where this is like xn and this is xn plus 1. So this sequence here is clearly non-decreasing, right? Therefore, xn is non-decreasing. So the sequence is non-increasing, is also non-decreasing. In summary, negative 1 power n times n is not a monotonic. Our aim is to prove that the following sequence is convergent to 0. Of course, we can certainly use the epsilon n criteria, but we are not going to do that here. First, we'll prove that this sequence is decreasing. So to this end, for any natural number n, 1/2 that square root of n is of course less or equal to square root of n plus 1. Next, this means that 1 over square root of n is in fact greater or equal to 1 over square root of n plus 1. Thus, the sequence 1 over square root of n is decreasing. Okay. Now, next we'll prove that this sequence is bounded, in fact. So to this end, let n be a natural number, since every natural number is at least 1, then the square root of n has to be at the square root of 1, which is also 1. And taking the reciprocal, we get this. As such, this sequence here is decreasing and bounded. All right, so the concept of subsequences will provide us a powerful tool. And from the previous result, it follows that the limit of this sequence is in fact the infimum of the set containing 1 over square root of n for every natural number n, and we can in fact show that this. All right, so let us consider the following sequence, which is not explicitly given, but in fact is defined recursively. We know the first term, and we know a relationship between two consecutive terms, namely y sub n plus 1 is 1 over 4 times 2 times yn plus 3. And we want to show that this sequence is actually converging to 3/2. So the first thing that I did was to compute a few values. So if n is 1, one gets, of course, that y sub 1 is 1. If you want to compute y sub 2, y sub 2 is 1 over 4 times 2 times 1 plus 3. So that'll be 1 over 4 times 5. So that'll be 5/4, which is 1.25. Knowing y2, we can construct y3. It's 1 over 4 times 2 times y sub 2 plus 3. And if you plug 5 over 4 here, you get 1.375. And I did a few values until 7. And I conjecture here, it is my conjecture that for every natural number k, y sub k is actually less than 3/2. So in fact, what this means is that this sequence is bounded. But of course, this is just a conjecture. We need to prove that, and we can try to prove this by using an inductive proof. So by induction, the base case holds since y sub 1 is 3/2, right? And of course 3/2 is less or equal to 3/2, so there's no problem here. I'm sorry, y sub 1 is, 1, sorry about that, y sub 1 is 1, and 1 is less than 3/2. Okay, so the base case holds. Now next, assume that y sub k is less or equal to 3/2 for some natural number k where k is at least 1. Then we know that y sub k plus 1 is 1 over 4 2 times y sub k plus 3. But that will be less or equal to 1 over 4 times 2 times 3/2 plus 3. And this is by the inductive hypothesis. Canceling the 3, we get 1 over 4 times 3 plus 3, which is 6 over 4, which is going to be 3/2. So clearly, in this case, if y sub k is less or equal to 3/2, then y sub k plus 1 is equal to 3/2. And so this verifies the inductive step. I shouldn't put this here yet. So this proves the claim, the conjectures. I should say here, this proves the conjecture. Now, so in summary, the given sequence y sub n, even though we don't know explicitly, we don't have a formula for y sub n, we do know that it is bounded. So this is a bounded sequence. Now, to apply the Monotone Convergence Theorem, we need to prove that it is monotonic, right? Now, in fact, I will prove by induction. So I claim, again, if you look at my table, it looks like this sequence here is increasing, right? 1.25, 1.375, and so on. So we can conjecture that the sequence is increasing. So, in other words, what this means is that for every natural number n, y sub n is less or equal to y sub n plus 1. I'll rewrite it in this form because it's easier to prove by induction when it's written this way. Okay, so as suggested, we will prove this by induction. When n is 1, we verify that y sub 1, which is 1, is clearly less or equal to y sub 2, which is 5/4. So thus the base case holds. Next, let us assume that y sub k is less than y sub k plus 1 for some natural number k where k is greater or equal to 1. Now, y sub k plus, let's say, y sub k plus 2 is really y sub 1/4 times 2 times y sub k plus 1 plus 3. And this is by assumption, by our inductive hypothesis, it's 1/4 times 2 times yk plus 3, right? By the inductive hypothesis. This is by the inductive hypothesis. And if you call this here star, and star is just yk plus 1. Okay, so we've proved that, so thus y sub k plus 2 is greater or equal to y sub k plus 1. And that gives us the desired result. So, in summary, in light of the above, yn is bounded, and monotone. By the Monotone Convergence Theorem, it is convergent to some real number y. Now, we don't know what y is. All we know is that the limit of yn when n is approaching infinity is indeed just y. Now, since we know that y sub n plus 1 is in fact 1 over 4 times 2 yn plus 3, and then because we know this, then we know that the limit as n is approaching infinity of y sub n plus 1 has to be y. Why? Because y sub n plus 1 is a subsequence of yn, and we know that and because it's a subsequence of the of that sequence, then it has to they have to converge to the same limit. Okay, now the limit of 1 over 4 to yn plus 3 as n is approaching infinity is going to be equal to 1 over 4 times 2y plus 3, which is in fact, this should be like this, right? So that'll be just 2y plus 3, I guess, over 4. And so this must be equal to y. In other words, 2y plus 3 must be 4y. And solving this equation, we get that 3 must be 2y, which means that y must be 3/2. So, in summary, we have shown that the sequence, the recursively defined sequence yn, is convergent. In fact, it's bounded and monotonic. It's convergent, and we have shown that its limit is precisely 3/2, even though we don't know the terms of our sequence explicitly. And that's pretty remarkable.